Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes.
Welcome back. My name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. You should have just finished watching my two videos, one on triangles, just as a review, and special triangles in trigonometry. All of that information is going to be very useful here. Also remember, you should have watched my videos on angles, specifically radian measure. If you don't have that down, it's going to suck. All right, so let's start into this. Trigonometric functions, a right triangle approach. Well, why is there a right triangle approach? Is there some other approach? The answer to that is yes. There are three different approaches to trigonometric functions. One is the right triangle approach. That's the approach that I actually prefer to start off with, at least. The second is a point definition, and the third is the unit circle definition. They all boil down to the same thing, so please don't feel overwhelmed. They all will essentially boil down to this triangle right here. So let me read this. The exploration of trigonometry is focused on the relationships between the sides of triangles, like these up above. So let's begin our journey. All right, let theta be an acute angle in a right triangle. And that reminds me, I want to change this angle right here to be called theta, not t. Just because I use thetas, I don't like using t's. It looks like a plus sign, that's why. Okay, so let theta be an acute triangle, or acute angle in a right triangle, and label the sides of the right triangle as follows. The hypotenuse for the hypotenuse, basically as follows in the picture above. Opposite for the side opposite the angle theta, and adjacent for the side adjacent to the angle theta. Then we will define the following. The sine of that angle theta is defined to be opposite over hypotenuse. So I'm going to go back up here. The sine of this angle theta. So trigonometric functions are functions of angles. You plug angles into them. And the sine of this angle theta is opposite divided by hypotenuse. That's it. The cosine is adjacent. I'm gonna mark that. Adjacent over hypotenuse. The tangent is opposite divided by adjacent. And if this is your first time taking trigonometry, or if you've never heard of trig before, I should be thorough here and just state this. The words for these are the sine, this is the cosine, this is the tangent, very critical in calculus. And then on the other side here, we had three more trigonometric functions. In other words, functions of angles. There's the cosecant. Let me go ahead and point at that. The cosecant. And then we have the secant. And then we have the cotangent. You see that word co comes up a lot. It's going to be important later on, but for right now, let's just not worry about it. All right. So notice there's a few things, there's actually quite a few things that should be noticeable here. One, sine is the opposite side of theta divided by the hypotenuse for the right triangle. And the cosecant is the reciprocal of that. It's the hypotenuse over the opposite. So if I drew that out in that picture, cosecant is hypotenuse, I'll use red here, hypotenuse divided by opposite, versus the sine, which is opposite over hypotenuse. Then we had the next one. The cosine was adjacent, again use green, adjacent over hypotenuse, versus the secant, which is hypotenuse over adjacent. And you get the idea now, right? So tangent was opposite over adjacent. Cotangent is adjacent over opposite. The question might come up, why do you need the cosecant, secant, or cotangent if they're just the reciprocals? That is a brilliant question. You need them for other operations, not just the ratios of the sides to a triangle. You need them for other operations. However, they don't get used as much as the sine and the cosine or the tangent. Of all 6 functions, the sine, the cosine get used the most, then the tangent, then I would say the secant, then the cosecant, then the cotangent. That's kind of the order with which they are used. Another question that often gets asked in my trig classes is why isn't the reciprocal of the sine called the cosine? And why isn't the reciprocal of the cosine called why don't we call the cosine something else, like a secant, and call its reciprocal the cosecant? Why isn't it like that? Well, the co part of the name on all these, let me just highlight those. This co part, that co, and that co part. They are not to do with reciprocal stuff. They're actually to deal with translations. So we will worry about that in a little bit. The main thing to know here are the definitions. Just sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. Some people remember this using a mnemonic. That's actually not a mnemonic, but just a word play here. They do SOHCAHTOA. Sorry, my pen just went. SOHCAHTOA. And that just tells us sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. Some people love that little way of remembering. I actually never knew it until I started teaching and students told me, and I thought, oh, okay, all right, that works. And it does, I guess. So here we go. Given the right triangle as follows, with hypotenuse 15, that's the hypotenuse is always opposite the 90-degree angle, and side length 5, state all the trigonometric function values of alpha. In other words, what's sine of alpha, what's cosine of alpha, what's tangent, all that stuff. Well, first of all, notice we're missing a side. That's not a big deal. We can totally find it because we can use the Pythagorean theorem. As I mentioned in the previous video, the Pythagorean theorem is going to be used all throughout trigonometry. So if for some reason, weird reason honestly, if you suck at the Pythagorean theorem, then trig is probably not going to be for you. But we'll call this missing side x for right now. 15 squared is x squared plus 5 squared. In other words, 225 is the same thing as x squared plus 25. Subtract 25. You get x squared is equal to 200, and that will tell us that x is equal to 10 root 2, right? Square root of 100 times the square root of 2. And it's positive because, again, it's a side length. So I'm going to fill that in here. This is 10 root 2. That's the first thing you need to do. Just get all your sides set up. And then you can start going through and doing the mathematics here. If you want to label these, you totally can. I don't normally, but you can if you want. You could call this the hypotenuse. You call this, in this case, it's the opposite, right? It's opposite the alpha that we're concerned with. And you can call this the adjacent side if you want to. That's probably the first time ever that I've done that, but you're totally welcome to do that. I don't think it's really that necessary, but so sine of alpha is opposite over hypotenuse. That's 10 root 2 over 15. Again, opposite of alpha divided by the hypotenuse. That's what it is. In fact, I should probably label that. It's opposite over hypotenuse, just to remind you, right? Because you just learned it, so it's better to do that. When you do this, make sure you reduce fractions. So they're both numerator and denominator are divisible by 5, so that's 2 root 2 over 3. The cosine of alpha, which is adjacent over hypotenuse, I'll draw that out. It's adjacent over hypotenuse. It's going to be 5 over 15. Well, again, reduce that down 1/3. Generally, I mark my students off for not doing arithmetic because the reality is you've learned it. You should use it. Tangent of alpha. That is opposite over adjacent. Let me write that in. Opposite over adjacent. The opposite of alpha is 10 root 2. The adjacent is 5. So 10 root 2 divided by 5. 10 times the square root of 2 divided by 5. So it's just 2 root 2. Once I set those up, I'm ready to find out what their reciprocals are. Remember, the reciprocal of the sine is the cosecant. The cosecant of alpha is just going to be the reciprocal, right? 3 over 2 root 2. Again, I don't bother getting rid of that or rationalizing that denominator. Now, here is a case where somebody could say, aha, I could tell you why you should rationalize that denominator, but I'm going to hold off for the moment. The secant of alpha is the reciprocal of the cosine, so it'll be 3. And the cotangent of alpha is the reciprocal of the tangent, so it's 1 over 2 root 2. If you need them in opposite over adjacent form, the cosecant is hypotenuse over opposite. So it's 15 over 10 root 2. It reduces down to 3 over 2 root 2. And so on and so forth down the line. Now, as I just kind of mumbled out there, I don't require my students to rationalize denominators, but here is a case where if a student was asked, or if a student was taking a different professor, they would probably be asked to rationalize this denominator. Because if you multiply both numerator and denominator by root 2, well, it does clean up. It doesn't clean up a lot, actually, but it does look a little bit better. It's 3 root 2 over 2 times 2, which is 4. It does look a little bit better. Not a lot, though. The other one, again, doesn't clean up. It'll become a root 2 over 4. Still, not that big of a deal. I wouldn't require my students to do that. All right, so we have found all of the trigonometric functions of alpha. Not bad, right? So if you've never had trig before, if you're like me, when I was a student and I was going to community college, I had never had trig in my life. And so when I went in to my trig class, I was hearing all of this for the first time. And it was actually a benefit, major benefit. If you see this for the first time, you've never seen it before, it's a huge advantage. People who have seen this stuff before tend to gloss over things. They're like, oh yeah, I totally know that. When in reality, they don't. They're kind of stuck in a mindset. So it's better to come to this with completely fresh eyes. Now this theorem right here, we've already stated, but it's good to state again. The cosecant and sine, they're just reciprocals of each other. So sine of theta is the same thing as 1 over cosecant, and the cosecant of theta is 1 over the sine. They're just, and again, remember, this is because sine is opposite over hypotenuse, and the cosecant is hypotenuse over opposite. The cosine and secant are reciprocals, and that is because the cosine is adjacent over hypotenuse, and the secant is hypotenuse over adjacent. And finally, the tangent and cotangent are reciprocals because, again, tangent is opposite over adjacent, and the cotangent is adjacent over opposite. I never tell maybe I should rephrase that. I should say, I don't want to tell my students to memorize a bunch of stuff about the cosecant, secant, and cotangent, because the most important trig functions are the sine, the cosine, and the tangent, and you should just know the reciprocals of those will be the cosecant, secant, and the cotangent. It's just faster than memorizing a bunch of different things. Now here's a really good question. I love these questions because you can't Chegg, look up on Chegg for something like this or photomath this or anything like that. Explain why there's no angle theta such that the cosecant of that angle would be 1/2. Why is it true that we cannot find an angle such that the cosecant of that angle is 1 over 2? One thing you should remember is all the trig functions are are ratios of sides of a triangle. That's it. That's all they truly are. So if you're to draw out a triangle here, a right triangle that is, and throw in there a theta wherever you want to, then you know this is opposite, this is adjacent, this is hypotenuse, and all of the trig functions are just telling you ratios of adjacents to opposites to hypotenuses. Or hypotenuse. I don't know if that's the plural of hypotenuse. It doesn't really matter. So anyhow, so why is it true that the cosecant of theta will never be 1/2? Well, what is cosecant? Cosecant is the reciprocal of the sine. And sine, remember, was opposite over hypotenuse. So cosecant must be hypotenuse over opposite. So I'm going to write that down. It's the hypotenuse over opposite. All right. Well, then if this was 1/2, that would mean the side opposite theta was twice as long as the hypotenuse. Let me write that down. You should see there's a logical fallacy there. There's something wrong, right? The side opposite, I highlighted the word side because it's the side of a right triangle. The hypotenuse is always the longest side. It can't be shorter than a side of the triangle. Hypotenuse is always longer than the sides. So I'm going to write that down. So the hypotenuse is always longer than the either side of the triangle. And that implies cosecant, CSC for cosecant of theta cannot be 1/2. Pretty good, solid argument as to why the cosecant can't be 1/2. All right, let's take a look at yet another property. In trigonometry, there's a ton, and really, honestly, more theorems than you could possibly handle. But luckily, you don't have to memorize all of them, but there are some critical ones you do have to remember. And here is one of them, called the ratio identities. The tangent is equal to the sine over the cosine. The tangent of theta is equal to the sine of theta over the cosine of theta. And because cotangent is the reciprocal of the tangent, well, you would flip that for the cotangent. Okay. The proof actually it technically can't be done with the language I'm using, but I'm still going to do it. So we know that the sine of theta is opposite, excuse me, over hypotenuse. And the cosine of that same angle is adjacent. It's supposed to be a J, but didn't quite work out. Is adjacent over hypotenuse. Well, we know that the tangent is opposite over adjacent, right? But if you multiply both top and bottom, or maybe I should say divide both top and bottom by hypotenuse, you would get the following. All I'm doing is dividing both numerator and denominator by the word hypotenuse, which is non-zero, by the way. That's important. And so opposite over hypotenuse, I have a way of writing that. That's called the sine. And that denominator, which says adjacent over hypotenuse, I have a way to write that. It's called the cosine. There you go. That is a very powerful theorem. Very, very powerful. And we'll use it quite a bit throughout trigonometry. So again, you should keep a piece of paper, or several actually, put it on the front of your notebook, whatever it is, with all the identities for trigonometry. As we go through, I could fill a single page with just identities by the time you get done with trig. Not to intimidate you. It's not actually that bad. You totally get used to it. But it is important that you really spend the time to get to know those values or those theorems. Now we're just baby stepping our way into trigonometry, so we haven't done a lot. I'm only going to do this extra example here, and then I'll stop this video, and then we'll go into another video next, which is evaluating trig functions for special angles, that is. But let's go ahead and just do this example. Find the remaining trigonometric function values. That's hard for me to say. Find the remaining trigonometric function values of theta if we know that theta is an acute angle and the cosine of theta is 20 over 29. Notice I didn't tell you that this theta isn't a right triangle or anything like that, but I hinted at it. It's an acute angle. So let's go ahead and just assume that theta is an acute angle within this right triangle. It's not a bad assumption, because if you just said, well, how do you know that it's within a right triangle? I would say, okay, let's pretend it's not. Let's just open an angle of theta. Okay, that's an acute angle. I hope you would agree. And they tell you the cosine of that angle, which is adjacent over hypotenuse. Well, that tells me that at some point that ray has to stop to become a line segment and has to drop in altitude. And the adjacent side, because remember, this is adjacent over hypotenuse, the adjacent side is going to be 20 and the hypotenuse will be 29. And then this tells me I can find all the remaining trig function values just by filling out the rest of this triangle, not the angles, just the sides. So let's go ahead and use the Pythagorean theorem to find this missing side x. Pythagorean theorem tells us that 29 squared should equal that x squared plus the 20 squared, right? Hypotenuse squared is equal to side squared plus side squared. That is 29 squared minus 20 squared should equal x squared. And this will take the square root of both sides so that we can go ahead and compute this. You're likely, not a lot of people are going to remember what 29 squared is. And in fact, I don't either. But when you square root it, 29 squared is 841. This is 400. That's 20 squared. And 841 minus 400 is 441. And you might have to grab a calculator for that, but I happen to know that's 21. So that's going to be 21. So I know that x is 21. Filled that in, and now we're ready to go. All right, so filling out the rest of the trig functions. So I always start with the same three. I'll go sine theta, cosine of theta, and tangent of theta. By the way, I use theta. Your instructor might use t's or a's or x's or alphas or betas. It just depends on what they like. I just like theta. It's just a habit of mine. And then I have their reciprocal functions, which is the, for the cosine, it's going to be the secant here. And for the tangent, it's going to be the cotangent. All right. So let's see. Sine is opposite, which is 21, over hypotenuse, 29. Cosine is adjacent, which is 20, over hypotenuse, which is 29. Tangent is opposite, which is 21, over adjacent, which is 20, and then take their reciprocals for the others. So cosecant will be 29 21st. Let's see, that's a cosecant. The secant itself is 29 20ths. And the cotangent is 20 21st. There you go. By the way, I should also mention, because these are nice clean numbers, that's yet another Pythagorean triple. Just like 3, 4, 5, 20, 21, and 29 are a Pythagorean triple. Okay, so anything else I want to tell you about this? Maybe. So if you're one of my students watching this, you might be a little bit freaked out saying, well, what if I'm working on an exam and you have the square root of 841 and then minus 400, and then you have the square root of 441. Am I supposed to remember that the square root of 441 is 21? The answer to that is no. I will keep the number somewhat manageable on an exam, so you don't need a calculator. That's all I really need to say there. I think that's it. All right, I'll see you in the next video.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much. That isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.